Hi, I'm Jong-Hoon Choi from Seoul National University. My presentation topic is feedback gain selection of discrete-time full-order flux observer suitable for high-speed operation of the induction machine. Outline is as follows. Presentation starts with the introduction. In the introduction, induction machine and flux observer structure are briefly analyzed, and the characteristics of the discrete-time full-order flux observer is investigated and the instability issue is analyzed. And third, feedback gain selection method is suggested to solve the instability. Also, the laboratory experiment was conducted and proposed method is verified. And the presentation ends with the conclusion. Vector control is generally implemented to achieve the high torque accuracy of the induction machine. It separates the current vector to flux and torque generating components along the direct and quadrature axis. Its orientation angle should be found precisely, but hardly measured in industrial applications. General vector control method uses the flux observer to estimate the flux orientation angle. Full order flux observer is broadly adopted, but its instability issue at the high speed region has been reported in many researches. Before analyzing the flux observer structure, induction machine plant is investigated. It has two stator and two rotor voltage equation, and total 8 variables are unknown values. But only 4 variables are the independence variables, so that all the values are uniquely determined. 4 equations can be represented as the state space vector form. System matrix A and the input matrix B can be simplified using the 2x2 matrices I and J. Stability of the induction machine is determined by the former state space equations. It has 4 system poles, and as you can see, all the pole location is on the left half plane irrespective of the machine speed. In addition, pole location determines the dynamics of the state error. Above a certain speed, error dynamics doesn't improve anymore. From now on, for the ease of the calculation, complex vector concept is adopted. D and Q axis components can be merged to a certain complex vector with J operator. By using the complex vector representation, equation dimension can be reduced by half. After applying the complex vector, the order of the determinant equation is reduced to 2. So the equation is changed to the quadratic form, which is easy to calculate the system poles. The remaining 2 poles are omitted because they are the complex conjugate of the solutions. Full order flux observer model is similar with the induction machine plants, but it has additional feedback term. Measurable state variables, which is stator current, are feedback to the observer. Its stability and the aerodynamics are determined by the determinant equation. Determinant equations of the flux observer has 4 gain values, and by setting the gain properly, characteristics could be changed. Conventional feedback gain selection method is suggested by Kubota. Observable poles are set as k times multiples of the original induction machine poles. Sum and product of the solutions are respectively k and k squared times of the original one. By solving these identical equations, feedback gain G1, 2, 3, and 4 can be derived. In DSP real-time application, system is in the discrete time domain, not the constant time. To check the discrete time domain stability, Euler approximation is implemented. There are three types of the approximation method: forward, backward, and the trapezoidal. But in the next slide, it is verified that only the forward Euler can be applied in the DSP systems. S to G transform equation is defined for each approximation method. Left half plane of the continuous time domain is also transformed. In the backward Euler method, stable area is extended to the right half plane. And in trapezoidal method, stable area is the same as the continuous time domain one. Therefore, if the system is stable in the continuous time domain, it always satisfies the stability in the discrete time domain. But these two methods are not feasible in the DSP environment because it requires calculation of the complicated 4x4 inverse matrix of the system matrix A. Contrary to the former two approximation methods, forward Euler doesn't need the inverse matrix so that it is easy to implement. However, the stable region in the discrete time domain is shrunk to a circle in the left half plane. So, high-speed operation of the induction machine would be unstable, as shown in the lower right figures. Circle radius is also the same as the sampling frequency. So, if the sampling frequency is quite low, the machine got more unstable. And for the Kubota gain selection method, larger K makes the system more unstable, even at the lower speed. Maes proposed a feedback gain selection method for the discrete time domain stability. Selected gain moves the system poles toward the real axis by delta. By setting the delta properly, instability can be solved, but the optimal delta value is different for every induction machine, and also it depends on the sampling frequency. Even if the stability criterion is satisfied, aerodynamics is still inconsistent according to the machine speed. Here, I proposed an observer feedback gain selection method to solve the former problems. All the system poles are located on a real axis at -k. Gain values can be derived by setting the sum and product of the determinants as -2k and k squared. It has no imaginary components, so that it can be applied in very low sampling frequency applications. And for the stability and dynamics, k values is set as machine speed with lower bound of the rotor time constant. As you can see, the board and step response proposed method has consistent and fast dynamics even at the high-speed operation. Generally, every flux observer has parameter sensitivity, and each sensitivity can be analyzed by getting the frequency response function. Lawrence first suggested this FRF analysis. By applying the proposed gain to the closed-loop models, sensitivity was compared to the one of the open-loop model, which is Kubota k=1 case. If the temperature rise is 100 degrees Celsius, resistance value is 1.4 times of the original one. In this situation, FRF according to the machine speed and load condition is compared. Proposed purple lines is always showing the robustness compared to the yellow, the open loop model. For the rotor resistance, open loop model is sensitive to the rotor resistance variation, but the proposed model shows robustness. Similarly, proposed model is robust to the mutual inductance Lm variation. In the leakage inductance variation, proposed model shows similar sensitivity to the voltage model. And also rotor leakage inductance variation shows similar sensitivity to stator one. Proposed gain method was experimentally verified in the laboratory environment. Contour divergence was observed at high-speed operation over the 4,700 RPM, which is the divergence speed limit at Kubota k=1.5 case. With Kubota gain selection method, machine speed was slightly under the divergence speed, which is 4,500 RPM. And you can see that the large resonance in the current and flux is observed. After reaching out the limit, resonance is getting bigger and bigger, and then finally motor control got unstable. But with the proposed gain selection method, you can see that the machine reaches the 7,000 RPM above the divergence limit, which is 4,700 RPM. And you can see that the motor control is still working well. Okay, so here is the conclusion of this presentation. Induction machine and the flux observer model were analyzed, and the observer instability issue in the discrete time domain was addressed. And also, the observer gain selection method for high-speed operation was proposed, and the parameter sensitivity also calculated with respect to the speed and the load condition. And finally, the stability at high-speed region was tested experimentally. Thank you.